Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that might keep you up tonight, but hopefully will lull you to sleep. Imagine you're holding a laser pointer. Simple enough, right? Now, imagine you're on a spaceship, accelerating to near the speed of light. You point that laser pointer forward. What happens to the light coming out of the laser? Does it travel faster than the speed of light because it's getting a boost from your spaceship's motion? The answer, perhaps unbelievably, is no. The light still travels at the speed of light relative to you, and relative to someone standing still on Earth watching you whiz by. This seemingly simple fact has profound implications that shape our understanding of space and time. It's a cornerstone of Einstein's theory of special relativity, and it's a deeply weird property of the universe that physicists are still trying to fully understand. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. So why is the speed of light so special? Why is it the universe's ultimate speed limit? And what does it tell us about the fundamental nature of space and time themselves? Let's dive in. To understand the strangeness of the speed of light, we first need to understand what quote 1 really means. In our everyday experience, speed is relative. If you're walking on a train moving at 50 miles per hour, your speed relative to the ground is your walking speed plus the train's speed. This seems obvious, and it's how things have always seemed to work. This intuitive understanding of relative speeds is based on what's known as Galilean relativity, named after Galileo Galilei, who first formalized it. In Galilean relativity, time is absolute and unchanging, and space is simply the stage on which events play out. It's a neat and tidy picture of the universe that works perfectly well for everyday speeds. However, in the late 19th century, physicists began to encounter some troubling discrepancies. James Clerk Maxwell, through his groundbreaking work on electromagnetism, had shown that light is an electromagnetic wave. Maxwell's equations predicted that the speed of light in a vacuum should be a constant value, approximately 299,792,458 meters per second, often rounded to 300,000 kilometers per second. This value, now denoted as c, is a fundamental constant of nature. Here's the kicker. Maxwell's equations didn't specify relative to what. This speed should be constant. This posed a serious problem. If light is a wave, it seemed reasonable to assume that it must be traveling through some medium, just like sound waves travel through air or water waves travel through water. This hypothetical medium was called the luminiferous ether, and physicists spent years trying to detect it. The most famous attempt was the Michelson-Morley experiment in 1887. Albert Michelson and Edward Morley designed an incredibly sensitive experiment to measure the Earth's velocity relative to the ether. They reasoned that as the Earth moved through the ether, the speed of light should be slightly different depending on whether it was travelling in the same direction as the Earth's motion or perpendicular to it. To their surprise, they found no difference whatsoever. The speed of light was the same in all directions, regardless of the Earth's motion. This result was baffling. It was as if you were on a boat, and no matter how fast the boat moved, the waves always travelled at the same speed relative to you. This was completely at odds with Galilean relativity and the intuitive understanding of how speed should add up. Now, let's pause for a moment and think about the implications of this. Imagine you're throwing a baseball on that same train. If you throw the ball forward at 50 miles per hour while the train is moving at 50 miles per hour, someone standing still outside the train would see the ball moving at 100 miles per hour. But if you were somehow able to throw a beam of light forward at the speed of light while on the train, that outside observer would still see the light moving at only the speed of light, not twice the speed of light. It's as if the universe has a built-in speed regulator that prevents anything from exceeding c. This is where Albert Einstein enters the picture. In 1905, Einstein published his groundbreaking paper on special relativity, which revolutionized our understanding of space and time. Einstein took a radical approach. Instead of trying to salvage the concept of the ether, he simply accepted the experimental evidence that the speed of light is constant for all observers regardless of their motion. He made two key postulates. 1. The laws of physics are the same for all observers in uniform motion, inertial frames of reference. 2. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. From these two seemingly simple postulates, Einstein derived a whole host of mind-bending consequences. One of the most important is that time and space are not absolute, as Newton and Galileo had assumed. Instead, they are relative and intertwined. The faster you move through space, the slower you move through time, relative to a stationary observer. This is known as time dilation. Conversely, the faster you move, the shorter distances become in the direction of your motion, relative to a stationary observer. This is known as length contraction. Think about it this way. Imagine you're on a spaceship traveling at 99.9% the speed of light. If you measure the length of your spaceship, it will appear to be the same as when you're at rest. But to someone on Earth watching you zoom by, your spaceship will appear to be drastically shorter, compressed in the direction of motion. And if you have a clock on your spaceship, it will appear to be ticking much slower than a clock on Earth. The amount by which time dilates and length contracts is determined by a factor called the Lorentz factor, which depends on your speed relative to the speed of light. As your speed approaches the speed of light, the Lorentz factor approaches infinity. This means that time slows down to a standstill and length contracts to zero in the direction of motion. This is why nothing with mass can actually reach the speed of light. It would require an infinite amount of energy. So the speed of light isn't just some random number. It's a fundamental constant that dictates how space and time are related. It's the ultimate speed limit of the universe, and it's a consequence of the fact that space and time are not absolute but are relative and intertwined. It means that the universe looks different depending on how fast you're moving. It's a deeply strange and counterintuitive idea, but it's been confirmed by countless experiments. But what is it about light that makes it so special? Why is it the yardstick by which we measure the fabric of space-time? That's a question that takes us deeper into the nature of electromagnetism and the quantum world, which we'll explore in the next chapter. Now let's consider the practical implications of all this. Special relativity isn't just some abstract theory with no real-world applications. It's essential for many of the technologies we rely on every day. For example, the Global Positioning System, GPS, relies on a network of satellites orbiting the Earth. These satellites are moving at high speeds relative to the Earth's surface, and their clocks experience time dilation due to both their speed, special relativity, and the Earth's gravitational field, general relativity, which we'll get to later. If these relativistic effects were not taken into account, GPS systems would be inaccurate by several meters per day, rendering them useless. So the next time you use your phone to navigate somewhere, remember that you're relying on Einstein's theory of relativity to get you there. In the next chapter, we'll delve deeper into the nature of light itself. What exactly is light, and why does it travel at this constant speed? We'll explore the wave-particle duality of light, the concept of photons, and the relationship between light, electromagnetism, and the very fabric of space-time. We'll see how light isn't just a wave or a particle, but something even more fundamental, a ripple in the electromagnetic field that permeates the entire universe. Okay, buckle up, because now you're probably asking, quote 2. It's a fair question, and the answer, well, it involves a bit of electricity, a dash of magnetism, and a whole lot of waving. Imagine dropping a pebble into a still pond. Ripples spread outward, right? These ripples are waves, disturbances that carry energy through the water. Light, in a way, is similar. It's an electromagnetic wave, a disturbance that carries energy through space. But instead of water, it's disturbances in electric and magnetic fields that are waving. Think of an electric field as an invisible force field surrounding any electrically charged object. A positive charge creates a field that pushes other positive charges away. A negative charge creates a field that pulls positive charges towards it. Now, picture a magnetic field, like the one around a magnet. It exerts forces on other magnets and moving electric charges. Here's the cool part. These electric and magnetic fields aren't separate. They're intertwined. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. It's a self-perpetuating cycle, a cosmic dance of push and pull. Now, imagine wiggling an electrically charged particle, like an electron. This wiggling creates a changing electric field. That changing electric field, in turn, creates a changing magnetic field. And that changing magnetic field creates, you guessed it, another changing electric field. This process continues, with the electric and magnetic fields constantly generating each other, propagating outwards as an electromagnetic wave. That, my friend, is light. This wave has a few key properties. First, there's the wavelength, the distance between two crests, or two troughs, of the wave. Think of it like the distance between two successive ripples in our pond. Second, there's the frequency, which is the number of wave crests that pass a given point per second. Imagine counting how many ripples hit a specific spot on the pond each second. The speed of light, c, is related to the wavelength and frequency by a simple equation. c equals wavelength times frequency. This means that light with a shorter wavelength has a higher frequency and vice versa. But no matter what the wavelength or frequency, the speed remains constant. Approximately 299,792,458 meters per second. That's fast. Really fast. Now you might be thinking, okay, electromagnetic waves, but I only see visible light. What about all the other stuff? and that's where the electromagnetic spectrum comes in. Visible light, the rainbow of colours we can see, is just a tiny sliver of the whole spectrum. Imagine a vast range of electromagnetic waves, from the incredibly long radio waves used to broadcast music and news, to the incredibly short gamma rays emitted by radioactive materials and powerful cosmic events. In between, you have microwaves, used in microwave ovens and communication, infrared radiation, which we feel as heat, ultraviolet radiation, which can cause sunburn, and X-rays, used in medical imaging. All of these are electromagnetic waves, differing only in their wavelength and frequency. They all travel at the speed of light, so light isn't just what we see, it's a fundamental form of energy that permeates the universe, carrying information and interacting with matter in countless ways. It's the messenger that brings us images from distant stars, the warmth of the sun on our skin, and the signals that power our smartphones. But how does this relate to space and time? Well, here's where things get really interesting. Remember how the speed of light is constant for all observers, regardless of their motion? This seemingly simple fact has profound implications for our understanding of space and time. Think about it. If you're in a car moving at 60 miles per hour and you throw a ball forward at 10 miles per hour, an observer standing still on the side of the road would see the ball moving at 70 miles per hour, 60 plus 10. That's Galilean relativity in action. Speeds add up, but light doesn't behave this way. If you're in a spaceship zooming past Earth at half the speed of light and you shine a flashlight forward, an observer on Earth wouldn't see the light beam travelling at 1.5 times the speed of light, 0.5 c plus c. Instead, they would still see it travelling at always. This means something has to give. If the speed of light is constant for all observers, then our intuitive notions of space and time as absolute and unchanging must be wrong. And this is where Einstein's genius truly shines. He realized that space and time are not independent entities, but rather are intertwined into a single, four-dimensional fabric called spacetime. Imagine a trampoline. If you place a bowling ball in the center, it creates a dip, right? This dip represents the curvature of space-time caused by the mass of the bowling ball. Now, if you roll a marble across the trampoline, it will curve towards the bowling ball due to the dip. This is analogous to how gravity works. Objects with mass warp space-time, and this curvature affects the motion of other objects. Einstein's theory of general relativity describes gravity not as a force, but as a curvature of space-time. Objects move along the curves in space-time, which we perceive as gravity. The more massive an object, the more it warps space-time, and the stronger its gravitational pull. So, what does this have to do with the speed of light? Well, the speed of light is not just a speed limit for objects moving through space. It's also a fundamental property of space-time itself. It's the conversion factor between space and time. Think of it this way. When you travel through space, you're also traveling through time. The faster you move through space, the slower you move through time, relative to someone who is standing still. This is time dilation. Again, but now with a deeper understanding. It's not just some weird effect that happens at high speeds. It's a consequence of the fundamental relationship between space and time. Imagine two identical twins. One twin stays on Earth, while the other embarks on a space journey at near the speed of light. When the travelling twin returns to Earth, they will be younger than their earthbound sibling. This isn't science fiction. It's a real effect that has been experimentally verified. The faster you move, the slower time passes for you, relative to a stationary observer. And what about length contraction? Well, just as time is relative, so is length. The faster you move, the shorter you appear to be in this direction of motion, again relative to a stationary observer. This is because space and time are intertwined, and changes in one affect the other. These effects, time dilation and length contraction, might seem bizarre and counterintuitive, but they are essential for understanding the true nature of space and time. They are consequences of the fact that the speed of light is constant for all observers, and that space and time are not absolute, but rather are relative and intertwined. Now you might be wondering, quote 4, that's a deep question, and one that philosophers and physicists have debated for centuries. But the answer, in short, is no. While our measurements of space and time are relative, the underlying space-time itself is an objective reality. Think of it like this. Imagine two people measuring the length of a table. One person uses inches, while the other uses centimeters. Their measurements will be different, but the table itself remains the same. Similarly, different observers may measure different times and distances, but the underlying space-time remains the same. So space and time are not just empty containers in which events happen. They are dynamic and interconnected, shaped by the presence of matter and energy. They are relative, but also objective. They are the fabric of the universe, and understanding their true nature is key to understanding the universe itself. But wait, there's more. We've explored special relativity, which deals with observers in uniform motion. But what about gravity? What about accelerating observers? That's where general relativity comes in, and it's an even wilder ride. Are you ready to delve deeper into the warped world of space-time? You accelerate. Feel that pressure pushing you back into your seat. It's a familiar sensation, isn't it? A subtle discomfort, a gentle but insistent reminder that you are no longer at rest. That's acceleration. It's not just speed, the sheer, raw velocity of hurtling through space. It's the change in speed, the constant push, the relentless increase. You can be moving incredibly fast, a blur against the backdrop of the cosmos. But if your speed is constant, if you're cruising along at a steady clip, you're not accelerating. You're just moving. Now consider what happens when you accelerate in the context of space-time. That's where things get truly interesting, where the familiar laws of physics begin to bend and twist into something almost unrecognizable. Remember our discussion of general relativity, the elegant, almost poetic way Einstein redefined gravity, not as a force pulling things together, but as a curvature of space-time. Well, acceleration and gravity are deeply intertwined, locked in a cosmic dance. Einstein formulated the equivalence principle, which states that the effects of gravity are indistinguishable from the effects of constant acceleration. It's a cornerstone of modern physics, a mind-bending concept that challenges our fundamental understanding of the universe. Think about it. You're sitting in a chair on Earth. You feel the weight of your body pressing down, the force of gravity pulling you towards the planet's core. It's a constant, unwavering pressure, a silent reminder of Earth's immense mass. Now, imagine you're in a rocket, far out in the emptiness of space, accelerating upwards at a constant rate of 9.8 meters per second squared, the same rate at which gravity pulls you down on Earth. The engines roar, a controlled explosion pushing you forward faster and faster. You would feel the exact same sensation, a force pushing you into your seat, the same pressure, the same feeling of being anchored to something solid. You couldn't tell the difference between being at rest in a gravitational field and accelerating through empty space. Close your eyes. Can you feel the difference? No, you can't. It's almost unsettling, isn't it? A voice echoes in your mind, the voice of your physics professor, Dr. Eleanor Vance. You remember her lectures, her passionate explanations, the way her eyes would light up when she talked about Einstein. That we can't distinguish between these two fundamentally different scenarios. This equivalence is profound. It suggests that gravity isn't some external force acting on objects, but rather a consequence of the geometry of space-time itself. Massive objects warp space-time, creating a kind of cosmic dimple, and this warping is what we perceive as gravity. Imagine a bowling ball placed on a stretched rubber sheet. It creates a dip, and if you roll a marble nearby, it will curve towards the bowling ball. That's a crude analogy, but it captures the essence of how gravity works. Acceleration, in turn, is a way of experiencing this warped space-time, of navigating its curves and contours. Now let's ramp up the thought experiment. Imagine you're in that accelerating rocket, moving faster and faster through space. The stars outside are beginning to streak, blurring into lines of light. As you accelerate, you might intuitively think that your speed can just keep increasing indefinitely. You picture yourself leaving the solar system behind, then the galaxy, then the local cluster, all at ever-increasing speeds. But remember that cosmic speed limit, the speed of light, c. It's the ultimate barrier, the unbreakable law of the universe. You can never reach it, no matter how hard you accelerate, no matter how much fuel you burn. Quote 7. Eleanor's voice whispers again. To be so close yet so far. To be forever chasing something you can never catch. But what does never reach it mean in the context of space-time? It means that as you approach the speed of light, your experience of time changes dramatically relative to someone who is not accelerating, someone who is in what we consider a relatively stationary position in space. Time, that seemingly constant and immutable measure, becomes fluid, malleable, subject to the whims of velocity and gravity. Think back to the twin paradox. One twin stays on Earth, living a normal life, experiencing the familiar rhythm of days and nights. The other twin takes a high-speed rocket trip, hurtling through space at a significant fraction of the speed of light. When the traveling twin returns, they are younger than the twin who stayed behind. This isn't just a theoretical curiosity. It's a real effect that has been experimentally verified using atomic clocks. But the twin paradox usually involves constant velocity. What happens when we introduce acceleration? Let's adjust the scenario. Instead of a simple out-and-back trip at constant speed, imagine the traveling twin accelerates away from Earth at a significant rate, feels the crushing force pushing them into their seat, then decelerates, the familiar pressure reversing as they slow down to turn around. Then they accelerate again back towards Earth, feeling the pressure once more, finally decelerating to a stop. All this acceleration drastically changes the space-time path of the traveling twin, creating a complex and convoluted trajectory. How does this affect the flow of time for each twin? The math gets complicated, filled with tensors and integrals and equations that would make your head spin. But the basic principle remains the same. The more curved the space-time path, the slower time passes relative to a less curved path. The accelerating twin experiences a more dramatically curved path through space-time due to their constant changes in velocity. The Earthbound twin, remaining in a relatively constant gravitational field and at a relatively constant velocity, experiences a straighter path. Their journey through space-time is less dramatic, less distorted. Therefore, the accelerating twin will still age more slowly than the Earthbound twin. The greater the acceleration, the greater the time dilation. The more intense the curves in their space-time path, the greater the difference in their ages upon reunion. But here's where it gets even more mind-bending. Let's push this to an extreme, to the very edge of what's possible, at least in theory. Imagine you're accelerating in your rocket at a constant rate, a relentless, unwavering push. As you accelerate, you look out the window. What do you see? According to special relativity, the universe ahead of you appears to be blue-shifted. The light waves are compressed, making them appear bluer, more energetic. It's as if the universe is rushing towards you, eager to meet you. Behind you, the universe appears red-shifted. The light waves are stretched, making them appear redder, less energetic. It's as if the universe is receding, fading away into the distance. This is the relativistic Doppler effect, a consequence of your relative motion. But now factor in general relativity and the equivalence principle. Your acceleration is equivalent to being in a gravitational field. And what happens to light in a gravitational field? It bends. Light emitted from a strong gravitational field loses energy as it climbs out, resulting in a redshift. Conversely, light falling into a gravitational field gains energy, resulting in a blue shift. So as you accelerate, you're experiencing both the relativistic Doppler effect and the gravitational effects of your equivalent gravitational field. The blue shift ahead of you is amplified by the gravitational blue shift, creating an even more intense concentration of energy. The red shift behind you is amplified by the gravitational redshift, causing the universe to fade even more rapidly into the darkness. Now, imagine accelerating for a very, very long time. Years turn into decades, decades into centuries, centuries into millennia. As you approach the speed of light, though, remember, you can never actually reach it, the blue shift ahead of you becomes extreme. The energy of the photons hitting your rocket increases dramatically. The universe ahead of you starts to appear incredibly bright and hot, a blinding inferno of light and energy. Behind you, the opposite happens. The redshift becomes extreme. The energy of the photons hitting your rocket decreases dramatically. The universe behind you starts to fade into darkness, into an absolute impenetrable blackness. It's as if you're leaving the past behind, severing your connection to everything that was. What's happening? You're essentially running into the future ahead of you and leaving the past behind you. Your acceleration is warping space-time so severely that you're experiencing time dilation on a cosmic scale. You are, in a sense, becoming unstuck in time. Imagine the perspective, Eleanor's voice muses. Quote 11. This isn't just a theoretical exercise. These effects, while subtle at everyday accelerations, become significant at relativistic speeds and in strong gravitational fields. They have real-world consequences, influencing everything from the behavior of particles in particle accelerators to the evolution of the universe itself. GPS satellites, for example, require incredibly precise timekeeping, and relativistic effects must be taken into account to ensure accurate positioning. Now, consider this. If acceleration warps your perception of time, and gravity is equivalent to acceleration, what does this tell us about the nature of time itself? Is time a fixed, immutable quantity, a universal constant, or is it something more fluid, more malleable, something that can be stretched and compressed by gravity and acceleration? We've seen that time is relative, that it depends on your motion and your location in space-time. But is there something more fundamental, something underlying this relativity? Is there a deeper level of reality where time, as we perceive it, simply ceases to exist? A realm beyond our comprehension, where the very fabric of reality is woven from something other than the linear progression we call time. These are the kinds of questions that physicists and philosophers grapple with today. And while we don't have all the answers, the journey of exploration is what makes science so exciting. The constant questioning, the relentless pursuit of knowledge, the willingness to challenge our assumptions. Let's shift our perspective again. We've been focusing on individual observers and their experiences of space-time, but what about the universe as a whole? How does space-time behave on the larger scales? To understand this, we need to delve into the realm of cosmology, the study of the origin, evolution, and ultimate fate of the universe, the grandest of all questions. Are you ready to zoom out? You're standing at the edge of a cosmic abyss, aren't you? Peering into the implications of relative time, wondering if there's something more fundamental lurking beneath the surface. You feel the ground shifting, the very notion of now becoming slippery. Well, take a deep breath. We're about to zoom out, way, way out. Let's consider the universe on the grandest scale imaginable. Forget planets, stars, even galaxies for a moment. Think about the observable universe, that sphere of space, roughly 93 billion light-years across, containing everything we can potentially see, given the finite speed of light and the age of the universe. Why? Quote, just while. Because the universe has been expanding since the Big Bang, about 13.8 billion years ago, and it's not just expanding, it's accelerating. This expansion means that the most distant galaxies are receding from us at speeds approaching and even exceeding the speed of light. Quote 13, you might object. Quote 14, excellent question. And the answer reveals another crucial piece of the puzzle. It's not that these galaxies are moving through space faster than light. It's that the space between us and them is expanding, carrying them along for the ride. Think of it like ants on a rubber band being stretched. The ants themselves aren't moving quickly, but the distance between them increases as the rubber band expands. This expansion has profound consequences. Light emitted from galaxies beyond a certain distance will never reach us. The space between us is expanding too quickly. These galaxies are effectively beyond our cosmic horizon, forever out of reach. Think about that for a moment. There could be countless galaxies, even entire universes existing beyond our observable horizon, completely inaccessible to us. We can't see them, we can't interact with them, we can't even know they're there directly. It's a humbling thought, isn't it? Now let's bring time back into the picture. As the universe expands and accelerates, what happens to time itself? Does it expand along with space? Does it have a beginning and an end, just like the universe is believed to? The answer, frustratingly, is that we don't know for sure. Our current understanding of physics breaks down at the very beginning of the universe, at the moment of the Big Bang. The equations predict a singularity, a point of infinite density and temperature, where the laws of physics as we know them cease to apply. What happened before the Big Bang? Was there a before? Did time even exist then? These are questions that push us to the very limits of our knowledge. Some physicists proposed that the Big Bang wasn't the beginning of everything, but rather a transition from a previous state. Perhaps our universe is just one of many, existing in a vast multiverse. Maybe these universes are constantly popping into and out of existence like bubbles in a cosmic foam. These are fascinating ideas, but they're largely speculative. We don't have any direct observational evidence to support them, but I highlight the fact that our understanding of time is intimately linked to our understanding of the universe as a whole. Consider the concept of cosmological time. This is a way of measuring time based on the expansion of the universe. We can use the cosmic microwave background, CMB, the afterglow of the Big Bang, as a kind of cosmic clock. By studying the CMB, we can infer the age and expansion rate of the universe. But even cosmological time is relative. An observer in a different part of the universe, experiencing a different gravitational field or moving at a different velocity, would measure a slightly different age for the universe. So, where does this leave us? We've explored the relativity of time, the curvature of space-time, and the expansion of the universe. We've seen how time is intertwined with gravity, motion, and the very fabric of the cosmos. But have we gotten any closer to understanding what time actually is? Perhaps not in the traditional sense. We haven't found a single definitive answer. But maybe that's because the question itself is flawed. Maybe time isn't a fundamental entity, but rather an emergent property of the universe, arising from the interactions of matter and energy. Think about it like temperature. Temperature isn't a fundamental property of individual atoms. It's a measure of the average kinetic energy of a collection of atoms. It emerges from the collective behavior of many particles. Could time be similar? Could it be an emergent property of the universe, arising from the interactions of countless particles and fields? Some physicists believe so. They're exploring ideas like quantum gravity, which attempts to reconcile general relativity with quantum mechanics, the theory that governs the behavior of matter at the subatomic level. One of the key challenges in quantum gravity is the problem of time. In general relativity, time is a dimension of space-time inextricably linked to space. But in quantum mechanics, time is treated as a background parameter, something that flows uniformly and independently of everything else. Reconciling these two views of time is one of the biggest unsolved problems in physics, but some promising approaches are emerging. For example, some theories suggest that time emerges from entanglement, a bizarre phenomenon in quantum mechanics where two particles become linked together in such a way that they share the same fate no matter how far apart they are. Imagine two entangled particles. If you measure the properties of one particle, you instantly know the properties of the other, even if they're on opposite sides of the universe. This instantaneous connection seems to violate the speed of light, but it doesn't transmit any information, so it doesn't actually break the laws of physics. Some physicists believe that entanglement may be the key to understanding the nature of time. They propose that time emerges from the increasing entanglement between different parts of the universe. As the universe evolves, more and more particles become entangled, creating a kind of cosmic network. This network, they argue, is what gives rise to our perception of time. This is a radical idea, but it's consistent with the fact that time seems to be intimately linked to entropy, the measure of disorder in the universe. As the universe expands and evolves, entropy increases, and as entropy increases, so does our perception of time. So, is time an illusion? Is it simply a byproduct of our consciousness? Or is it a fundamental aspect of reality, woven into the very fabric of the cosmos? The answer, as always, is that we don't know for sure. But by exploring these questions, by pushing the boundaries of our knowledge, we're getting closer to understanding the true nature of space and time. And perhaps, in the process, we'll discover something even more profound about ourselves and our place in the universe. We've travelled far, haven't we? From the simple observation that light speed is constant, to the mind-bending implications of quantum entanglement and the accelerating expansion of the universe. But the journey isn't over. In fact, it's just beginning. What about the possibility of time travel, and what are the philosophical implications of a universe where time might not be what we think it is? These are the questions we'll grapple with next. Prepare yourself. The rabbit hole goes deeper. You stand at the precipice of another question, a question that has haunted philosophers and physicists alike. Can you travel through time? The very notion is steeped in paradox, riddled with inconsistencies that make even the most ardent proponents of theoretical physics pause. But let's not shy away from the challenge. Let's dive headfirst into the swirling currents of temporal mechanics and see what we can find. First, a crucial distinction. We aren't talking about simply experiencing time, which you are right now, at a rate of 1 second per second, at least relative to your own frame of reference. We're talking about moving through time at a different rate than that dictated by your local inertial frame. Can you somehow skip ahead, or rewind the cosmic clock? Special relativity, with its time dilation effects, offers a tantalizing glimpse of possibility. Remember the accelerating spaceship from the last chapter, the one with the extreme blue shift ahead and red shift behind? Imagine that spaceship capable of near light speed acceleration, sustained for a significant period. For you on board, perhaps only a few years would pass, but back on Earth, centuries, millennia even, could elapse. You'd effectively be travelling into Earth's future. Is this time travel? In a sense, yes. You've moved into a future that would have been inaccessible to you had you remained in your original frame of reference. But it's a one-way trip. You can't go back, and it relies on the asymmetry of acceleration. Acceleration is not relative. You can always tell if you're accelerating without looking outside your spaceship. This breaks the symmetry needed for true bidirectional time travel. What about general relativity? Gravity, as we know, warps space-time. Could we manipulate gravity, create a shortcut through space-time, a wormhole, that would allow us to jump between different points in time? The idea is seductive. A wormhole, also known as an Einstein-Rosen bridge, is essentially a tunnel connecting two distant points in space-time. Imagine folding a piece of paper in half and poking a hole through both layers. That hole represents the wormhole, a shortcut that bypasses the conventional distance between the 2 points on the paper. Theoretically, if you could travel through a wormhole, you could emerge at a different location in space and a different point in time. This, unlike the relativistic spaceship, could potentially allow for travel to the past. But here's the rub. Wormholes, if they exist at all, are likely to be incredibly small, unstable, and require exotic matter with negative mass-energy density to keep them open. We've never observed negative mass-energy density. All the matter and energy we know of has positive mass-energy density. Negative mass-energy density would have the bizarre property of being repelled by gravity, rather than attracted. It's the stuff of science fiction, not science fact. At least, not yet. Even if we could find or create exotic matter and stabilize a wormhole, there's no guarantee it would be a time machine. It might simply connect 2 distant points in space at the same point in time. To turn it into a time machine, one end of the wormhole would need to be accelerated to near light speed relative to the other, or placed in a stronger gravitational field. This would induce time dilation, creating a temporal offset between the 2 mouths of the wormhole. Now imagine stepping into one end of the wormhole. You emerge at the other end, but at a different time. You've travelled through time. But here's where the paradoxes rear their ugly heads. The most famous, of course, is the grandfather paradox. If you travel back in time and prevent your grandparents from meeting, you would never have been born. But if you were never born, how could you have travelled back in time to prevent their meeting? It's a logical contradiction that seems to invalidate the very possibility of time travel. There are several proposed solutions to the grandfather paradox, none of which are entirely satisfactory. One is the self-healing timeline hypothesis. This suggests that the universe has a way of correcting any paradoxes that might arise from time travel. If you tried to prevent your grandparents from meeting, some unforeseen event would intervene, ensuring that they still got together. Perhaps a flat tire, a missed train, or a sudden change of heart would conspire to maintain the integrity of the timeline. Another is the many worlds interpretation of quantum mechanics. This suggests that every time a quantum event with multiple possible outcomes occurs, the universe splits into multiple parallel universes, each representing a different outcome. If you travelled back in time and prevented your grandparents from meeting, you wouldn't be changing your past. Instead, you'd be creating a new timeline, a new universe, in which you were never born. Your original universe, the one in which you were born, would remain unchanged. You'd simply be branching off into a different reality. A third possibility is that time travel is simply impossible. The universe, in its infinite wisdom, may have erected safeguards to prevent us from tampering with the past. Perhaps the laws of physics themselves conspire to make time travel an unattainable dream, but let's not be too quick to dismiss the idea. Nature is often far stranger and more imaginative than we can possibly conceive, and who knows what secrets lie hidden within the fabric of space-time waiting to be discovered. Consider another thought experiment. Closed time-like curves, CTCS. These are theoretical paths through space-time that loop back on themselves, allowing an object to return to its own past. Imagine a roller coaster that starts and ends at the same point in space and time. Travelling along a CTC would be like riding that roller coaster, endlessly looping through time. CTCS are predicted to exist in certain solutions to Einstein's field equations. particularly around rotating black holes or hypothetical constructs like cosmic strings. However, their existence is highly speculative, and even if they do exist, it's not clear whether they would be traversable. The problem is that CTCs, like wormholes, are prone to paradoxes. If you could travel along a CTC, you could, in principle, interact with your past self, leading to all sorts of causal inconsistencies. One attempt to resolve these paradoxes is the Novikov self-consistency principle. This principle states that if time travel is possible, then the laws of physics must somehow conspire to prevent paradoxes from occurring. In other words, you might be able to travel back in time, but you wouldn't be able to change anything that would lead to a contradiction. The universe would somehow adjust events to ensure that the timeline remains consistent. For example, if you tried to kill your past self, something would inevitably go wrong. Perhaps your gun would jam, or you would slip and fall, or a sudden gust of wind would blow your shot off course. The universe would find a way to prevent you from succeeding, not because it has a will of its own, but because the laws of physics demand it. The Novikov self-consistency principle is a fascinating idea, but it's also deeply unsatisfying. It suggests that we have no free will when travelling through time, that our actions are predetermined by the need to avoid paradoxes. It turns us into mere puppets of space-time, with no control over our own destinies. So, where does this leave us? Time travel remains a tantalizing possibility, a subject of endless fascination and debate. Special relativity offers a glimpse of unidirectional time travel to the future, while general relativity raises the prospect of bidirectional time travel through wormholes or along closed time-like curves. However, these possibilities are fraught with difficulties, both theoretical and practical. Wormholes and CTCs may not exist, and even if they do, they may be unstable or untraversable. And even if we could travel through time, we would have to contend with the paradoxes that inevitably arise, such as the grandfather paradox. Perhaps the universe is inherently self-consistent, and the laws of physics will always conspire to prevent us from changing the past. Or perhaps the many worlds interpretation is correct, and every time we attempt to alter the timeline, we simply create a new parallel universe. Ultimately, the question of whether time travel is possible remains open. It's a question that will continue to challenge our understanding of space, time, and the very nature of reality. And as we delve deeper into the mysteries of the universe, we may one day unlock the secrets of temporal mechanics and finally answer the age-old question: can we truly travel through time? But maybe, just maybe, the question we should be asking is not, can we travel through time, but should we? The potential consequences of tampering with the past are so profound, so potentially catastrophic, that perhaps it's best to leave the cosmic clock undisturbed. For now you remain firmly planted in the present, hurtling through space-time at an astonishing speed, carried along by the relentless flow of time, and that in itself is a pretty remarkable journey. But what is time really? We've explored how it behaves, how it's relative, how it's intertwined with space. But what is it fundamentally? Is it a dimension like space or something else entirely? That's the question we'll tackle next. You've pondered wormholes, danced with paradoxes, and even considered the ethical quandaries of altering the past. But now, let's pull back from the specifics of how time might be manipulated and focus on a more fundamental question. What is time anyway? Professor Anya Sharma leaned back in her worn leather chair, the scent of old books and brewing tea thick in the air. Sunlight streamed through the tall windows of her office, illuminating dust motes dancing in the air like tiny ephemeral galaxies. She swiveled slightly, her gaze settling on the intricate hand-drawn diagrams of space-time manifolds that adorned one wall. She'd spent decades wrestling with this question, and the weight of its complexity was etched into the fine lines around her eyes. Quote, 17. She mused aloud, more to herself than to the empty room. Quote, 18. Is it a dimension? That's the prevailing view in physics, especially since Einstein. Space you understand intuitively. You can move forward, backward, left, right, up, and down. 3 directions, 3 dimensions. But what if time is just another direction? A 4th dimension through which we are constantly moving. Anya picked up a well-worn Rubik's Cube from her desk, idly twisting its coloured squares. We're so comfortable with the idea of spatial dimensions, she continued, her voice a low murmur. We can visualize them, map them, navigate them. But time is different. It's elusive, intangible. We can't go back to yesterday in the same way we can walk back to the corner store. Think of it like this: a photograph. It's a 2-dimensional representation of a 3-dimensional scene. The photograph captures a slice of that 3D world at a single instant. Now, imagine a stack of photographs, each taken at a slightly later time. Stack them together, and you begin to build a 4-dimensional object, a space-time representation of that scene evolving through time. She set the Rubik's Cube down and picked up a stack of index cards, each bearing a different image. A baby's first steps, a couple's wedding day, an elderly woman blowing out birthday candles. Each card is a snapshot, a fleeting moment frozen in time, she explained, fanning the cards out like a deck of playing cards. But when you stack them together, you get a story, a life, unfolding. That's space-time, a tapestry woven from every event that ever was, is, or will be. In this view, you aren't just existing in space, you are existing in space-time. Your life, from birth to death, is a continuous, quote 23, tracing a path through this 4-dimensional landscape. Every event that ever happened, or ever will happen, is already, quote 24, in space-time, laid out like a vast frozen tableau. Anya paused, a flicker of doubt crossing her face. She sighed. But does that feel right to you? Does it feel like you're simply tracing a predetermined path through a static, 4-dimensional block universe? Or does it feel like you are experiencing time as something flowing, something dynamic? This is where the trouble begins. The block universe view, while mathematically elegant and consistent with general relativity, struggles to account for our subjective experience of time's passage. Where is the double quote 27 in this static space-time? If everything is already double quote 28, then what makes this moment, this now, so special? Why do we remember the past but not the future? Anya remembered a conversation she'd had years ago with a bright-eyed, enthusiastic undergraduate named David. He'd been captivated by the block universe theory, but also deeply troubled by its implications. Dr. Vance once posed this very question to a particularly bewildered undergraduate. Quote 29, she said. Quote 30. David had frowned, pushing his glasses up his nose. Quote 31. He'd said, his voice filled with genuine concern, if everything is already there, then what's the point of even trying? What's the point of making choices, of striving for a better future, if it's all already predetermined? Anya had smiled gently. Ah, David, she'd replied. Quote, is that all it is? A trick of perspective? Are we simply limited to perceiving only a sliver of a reality that already exists in its entirety? Some physicists argue that the perceived quote 35 quote of time is an illusion, a byproduct of our brains processing information. Our memories create a sense of past, present, and future. But these are merely constructs of our consciousness, not fundamental properties of the universe itself. Anya considered this, tapping a pen against her teeth. Quote 36, she mused. Quote 37. Consider entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases in a closed system. A dropped glass shatters. It doesn't spontaneously reassemble. A star burns brightly, eventually exhausting its fuel. This increasing entropy gives time a direction, an arrow. We perceive the past as more ordered, the future as more disordered. But is this arrow of time inherent in the fabric of space-time, or is it merely a consequence of the initial conditions of the universe? Anya thought of a meticulously organized bookshelf in her office, gradually accumulating dust and clutter. Entropy is a powerful force, she acknowledged. It's the reason why we can distinguish between a video played forward and a video played in reverse. It's the reason why we remember yesterday, but not tomorrow. Think about it. The equations of physics are, for the most part, time-symmetric. This means that they work just as well if you run them forward or backward in time. A ball thrown in the air follows the same trajectory whether you're watching the video play forward or in reverse, ignoring air resistance, of course. So, if the fundamental laws of physics don't distinguish between past and future, where does the arrow of time come from? One popular explanation is that the early universe was in an incredibly low entropy state, a state of extreme order. As the universe expanded and cooled, entropy inevitably increased, creating the arrow of time that we experience. In this view, the arrow of time is not a fundamental property of space-time, but rather an emergent property arising from the statistical behavior of a vast number of particles. But this explanation raises another question. Why was the early universe in such a low entropy state to begin with? Was it simply a random fluctuation? Or is there some deeper underlying principle that favours low entropy initial conditions? Anya sighed again, running a hand through her greying hair. The question of initial conditions is a real sticking point, she admitted. It's like asking, why is there something rather than nothing? It's a question that borders on the metaphysical. These questions lead us to the very edge of our understanding. They touch upon the deepest mysteries of cosmology and quantum gravity, and they suggest that our intuitive notions about time may be profoundly wrong. Perhaps time isn't a dimension at all. Perhaps it's something else entirely. Some physicists propose that time is an emergent phenomenon, arising from the underlying quantum structure of space-time. Imagine that space-time isn't smooth and continuous, as general relativity suggests, but rather granular, composed of discrete, quote 43, of space and time. In this view, time isn't a fundamental building block of the universe, but rather a collective behavior of these underlying quanta, much like temperature is a collective behavior of molecules. Anya pictured a vast ocean, its surface appearing smooth and continuous from a distance. But up close, it's composed of countless individual water molecules, each interacting with its neighbours in complex ways. Quote 44, she mused. Quote 45. Think of it like this. You can't point to a single molecule and say, quote 46. Temperature is a property that emerges from the collective motion of many molecules. Similarly, time might be a property that emerges from the collective behaviour of the fundamental constituents of space-time. This idea is still highly speculative, and there's no definitive experimental evidence to support it, but it offers a tantalizing glimpse into a possible future where our understanding of time is radically different from what it is today. So, where does this leave you? You've explored the possibility of time travel, grappled with the block universe, and considered the arrow of time. You've seen that time might be a dimension, an illusion, or an emergent phenomenon. The truth is, we don't know for sure what time actually is. It remains one of the deepest and most challenging mysteries in physics. But that's what makes it so fascinating. The very act of questioning our assumptions about time can open up new avenues of thought and lead to a deeper understanding of the universe. Anya smiled, a genuine, heartfelt smile that reached her eyes. The beauty of science is not in finding all the answers, she said. It's in the relentless pursuit of those answers, in the constant questioning and exploration. It's in the journey itself. And perhaps, just perhaps, by unraveling the mystery of time, we can unlock secrets that were previously unimaginable. We might even, dare we say, learn to navigate the river of time itself with a bit more intention. But for now, let's just keep questioning, keep exploring, and keep dreaming. After all, the universe is full of surprises, and the nature of time may be the biggest surprise of all. Anya took a sip of her now cold tea, a thoughtful expression on her face. She knew the journey was far from over. The mystery of time would continue to beckon, to challenge, to inspire. What if our perception of time is intrinsically linked to consciousness itself? We'll explore that next. She leaned forward, her eyes gleaming with anticipation. That, she knew, was a rabbit hole worth diving into. You're left pondering the enigma of time, its arrow seemingly dictated by the relentless increase of entropy. But is that the whole story? Does our subjective experience of time, the feeling of its passage, arise solely from the thermodynamic laws governing the universe? Or is there something more at play, something intrinsically linked to consciousness itself? Dr. Vance, in one of her more philosophical moods, used to say, quote 49, think about it. A rock exists. Gowin, quote 50. But does it just experience time? Does it have a sense of past, present, and future? Probably not. Its existence is governed by physical laws, but there's no internal narrative, no subjective viewpoint colouring its perception. You, on the other hand, possess a rich inner life, a constant stream of thoughts, memories, and anticipations. This stream is your experience of time. Without consciousness, would time even matter in the same way? This brings us to a fascinating, albeit highly speculative area of research, the connection between consciousness and the flow of time. Some physicists and philosophers propose that consciousness isn't merely a passive observer of time's passage, but an active participant in its very creation. That sounds out there, you might be thinking. And you're right, It's on the fringes of established science, but bear with us. To understand this perspective, we need to delve into the realm of quantum mechanics and the observer effect. Remember the famous double slit experiment? When you observe which slit a particle passes through, its wave function collapses and it behaves like a particle. When you don't observe, it behaves like a wave passing through both slits simultaneously. The act of observation fundamentally alters the outcome. Now, some interpretations of quantum mechanics, particularly those leaning towards the quote 52 idea, suggest that it's not just any observation that causes the wave function to collapse, but observation by a conscious observer. This is where things get really interesting. If consciousness plays a role in collapsing wave functions, and wave functions describe the probabilities of different states in the universe, then consciousness could, in a sense, be shaping reality itself. And if reality is being shaped, then so is the flow of time, as time is inextricably linked to the unfolding of events in the universe. Professor Sharma, when pressed on this topic, offered a more nuanced view. It's not necessarily that consciousness creates time, but rather that our conscious experience filters and interprets the quantum information available to us, giving rise to our subjective sense of temporal flow. Think of it like this. The universe might be a vast ocean of possibilities, and our consciousness acts as a kind of lens, focusing our attention on a particular sequence of events, creating the illusion of a linear timeline. Imagine a vast branching tree, each branch representing a different possible future. Quantum mechanics suggests that all these branches exist simultaneously as possibilities. Your consciousness, according to this view, is constantly selecting which branch to follow, creating your individual timeline. This idea resonates with the concept of the present moment. What exactly is the present? Is it an infinitesimally small slice of time separating the past from the future? Or is it more of a subjective window, a zone of awareness that encompasses a brief duration? Our brains are constantly processing information, integrating sensory input, and constructing a coherent narrative of reality. This process takes time. There's a measurable delay between a stimulus and our conscious perception of it. This delay suggests that our experience of the present is not a snapshot, but a construction, a synthesis of past and present data. Consider the phenomenon of quote 54. If you see a flash of light followed immediately by a beep, your brain might perceive them as happening simultaneously, even if there's a slight delay between them. Your brain is actively binding these events together, creating a unified experience of the present. This binding process highlights the active role of consciousness in shaping our perception of time. We're not simply passively recording events, we're actively organizing them, interpreting them, and constructing a narrative that makes sense to us. But if our perception of time is a construct, does that mean it's an illusion? Not necessarily. It simply means that our experience of time is not a direct reflection of some objective, external reality. It's a product of our interaction with the universe, shaped by our brains and our consciousness. Now, let's circle back to entropy. We established that the arrow of time seems to align with the increase of entropy. But could it be that our conscious awareness of time's arrow actually reinforces this entropic trend? Think about how we interact with the world. We constantly make choices, perform actions, and create order out of chaos. We build structures, write books, and compose music. But every act of creation also generates entropy. Building a house requires energy, which dissipates as heat. Writing a book consumes resources, leaving behind a trail of waste. Could it be that our conscious efforts to create order in the world are actually contributing to the overall increase in entropy, thereby reinforcing our perception of time's unidirectional flow? It's a bit of a chicken and egg scenario. Does entropy drive our perception of time, or does our perception of time through our actions drive entropy? The answer, most likely, is both. There's a feedback loop at play, a complex interplay between the physical laws of the universe and the subjective experience of consciousness. This leads to some truly mind-bending questions. If consciousness is so intimately linked to our perception of time, what happens to our experience of time when consciousness is altered? Consider meditation. Experienced meditators often report a slowing down or even a complete cessation of the internal dialogue, the constant stream of thoughts that usually occupies our minds. In these moments, the sense of time can become distorted, elongated, or even disappear altogether. Similarly, near-death experiences often involve profound alterations in the perception of time. Some people report experiencing their entire lives flashing before their eyes, while others describe feeling as though they've entered a timeless realm. These altered states of consciousness suggest that our ordinary perception of time is not fixed or immutable. It's a flexible, adaptable construct that can be profoundly influenced by our mental state. So where does this leave us in our quest to understand what time actually is? We've explored the physics of time, from relativity to entropy. And now we've delved into the potential role of consciousness in shaping our experience of time. It's clear that time is not a simple, straightforward concept. It's a multifaceted phenomenon that touches upon some of the deepest mysteries of the universe and the human mind. Perhaps, as Dr. Vance often hinted, the true nature of time will only be revealed when we fully understand the nature of consciousness itself. And that, you realize, is a journey that has only just begun. The next step? To explore the philosophical implications of all this, and to consider what it means for our understanding of free will, determinism, and the very fabric of reality. Are we truly the authors of our own timelines, or are we merely passengers on a predetermined course? That, you suspect, will be a discussion for another chapter. You stand at the edge of the known, peering into the swirling mists of the unknown. Consciousness, you realize, might be more than just a passenger in the space-time vehicle. It might be a driver, a mechanic, or perhaps even the architect of the road itself. But what does this mean for the choices you make, the life you lead? Where does free will fit into a universe seemingly governed by immutable laws? This is the realm of philosophy, where questions are more valuable than answers, and where the journey of thought is the destination. Prepare yourself, because we're about to dive headfirst into the age-old debate of free will versus determinism, viewed through the lens of our space-time explorations. Determinism, in its simplest form, argues that every event, including your every thought and action, is causally determined by prior events. Think of it like a colossal chain reaction, stretching back to the Big Bang itself. Each link in the chain is inevitable, a direct consequence of what came before. In a deterministic universe, your feeling of choosing between coffee and tea this morning would be an illusion. The choice was already made, predestined by the precise arrangement of atoms in your brain and the universe at large. Does this sound bleak? Perhaps. But consider the implications for space-time. If the block universe theory is correct and all moments in time exist simultaneously, then your entire life, from birth to death, is already written. There's no room for deviation, no branching paths. You're simply experiencing a predetermined slice of space-time. Now let's throw a wrench into the gears of determinism. Quantum mechanics. Remember the observer effect? The act of observing a quantum system influences its behavior. Before observation, a particle exists in a superposition of states, a probabilistic cloud of possibilities. Only when you measure it does it, quote, 56, quote, into a definite state. Does this quantum weirdness offer an escape from determinism? Some physicists and philosophers believe so. They argue that the inherent randomness of quantum events introduces an element of unpredictability into the universe, a wiggle room for free will to operate. Perhaps your conscious intention can subtly influence the quantum processes in your brain, nudging you towards coffee instead of tea. But even if quantum mechanics introduces randomness, does that truly equate to free will? Imagine a coin flip. The outcome is random, but does the coin choose to land on heads or tails? Similarly, if your actions are simply the result of random quantum fluctuations, are you really in control? Or are you just a puppet dancing to the tune of chance? This is where the concept of compatibilism enters the stage. Compatibilists argue that free will and determinism are not mutually exclusive. They propose that you can be both determined and free, as long as your actions are caused by your own desires and beliefs, even if those desires and beliefs are themselves the product of prior causes. Think of it like this. You're sitting in a car. The car's movements are determined by its engine, its steering system, and the road it's on. But you, the driver, are still making choices about where to go, how fast to drive, and when to turn. Your choices are constrained by the car's capabilities and the road's layout, but they are still your choices. Compatibilism offers a comforting middle ground, a way to reconcile the scientific view of a law-governed universe with our deeply felt sense of agency. But it doesn't fully address the core question: where do your desires and beliefs come from? If they are ultimately the product of deterministic processes, are you truly free? Perhaps the answer lies in the emergent properties of complex systems. Your brain is an incredibly complex network of neurons, far more intricate than any car engine. It's possible that consciousness, and the free will that accompanies it, emerges from this complexity in a way that transcends the deterministic laws governing its individual components. Imagine a flock of birds. Each bird follows simple rules: stay close to its neighbors, avoid obstacles, and move in the same direction. Yet the flock as a whole exhibits complex coordinated behavior that is not predictable from the behavior of individual birds. The flock seems to have a mind of its own, even though it is simply the result of local interactions. Could consciousness be a similar emergent phenomenon? Perhaps free will is not a fundamental property of the universe, but rather a higher-level property that arises from the complex interactions within your brain. In this view, you are not simply a collection of atoms following deterministic laws, but a self-organizing system capable of making genuine choices. But let's not forget the influence of space-time itself. We've seen how gravity warps space-time, how acceleration affects time perception, and how the expansion of the universe shapes the very fabric of reality. Could spacetime also play a role in shaping your free will? Consider the concept of retrocausality, the idea that future events can influence past events. This is a highly speculative idea, but it has been explored in some interpretations of quantum mechanics. If retrocausality is possible, then your future choices could, in principle, influence your present state, shaping your desires and beliefs in subtle ways. Imagine that you're facing a difficult decision. You could choose one path which leads to a life of happiness and fulfillment, or another path which leads to regret and disappointment. If retrocausality is real, then the future you, living with the consequences of your choice, could send signals back in time, nudging you towards the path that leads to happiness. This is not to say that your future self is directly controlling your actions. Rather, the influence would be subtle, a gentle push in the right direction. It's like a whisper from the future, guiding you towards your best possible self. Of course, retrocausality is a controversial idea, and there is no definitive evidence to support it. But it highlights the interconnectedness of space-time and the potential for the future to influence the present. If space-time is not a rigid, static structure, but rather a dynamic, evolving entity, then the possibilities for free will become even more intriguing. So, where does this leave you? Are you a free agent, capable of making genuine choices? Or are you simply a puppet of determinism, acting out a predetermined script? The answer, as you might suspect, is not simple. The exploration of space-time has revealed a universe far more complex and mysterious than we ever imagined. The relationship between space, time, consciousness, and free will is a tangled web of possibilities, a puzzle that may never be fully solved. But perhaps the act of grappling with these questions is more important than finding definitive answers. By questioning the nature of reality, by challenging our assumptions about space, time, and consciousness, we can expand our understanding of ourselves and our place in the universe. You stand at the crossroads of science and philosophy, armed with the knowledge of space-time and the mysteries of consciousness. The choice is yours. Will you embrace the deterministic view, accepting that your actions are preordained? Or will you cling to the hope of free will, believing that you have the power to shape your own destiny? The universe awaits your decision, and perhaps in some small way, your decision will shape the universe in return. So, where does all of this leave us? You've journeyed through mind-bending concepts, grappled with paradoxes, and questioned the very nature of reality. You've stared into the abyss of the unknown, and perhaps the abyss has stared back. What conclusions can we draw from this whirlwind tour of space-time, consciousness, and free will? Are there any solid answers, or are we left adrift in a sea of possibilities? Perhaps the most unsettling possibility is that it's all an illusion, not in the sense of a cheap magic trick, but in a far more profound way. Consider the block universe. If all of space-time exists simultaneously, then past, present, and future are equally real. Your life isn't a journey unfolding moment by moment. Instead, it's a static, four-dimensional structure, like a sculpture carved from space-time itself. Where does this leave your sense of agency, your feeling of making choices? If your entire life is already, quote, 57, quote, then aren't you just acting out a predetermined script? You feel like you're deciding what to eat for breakfast, but in the block universe, that decision is already etched into space-time. It's as fixed as the pyramids of Giza. This is a deeply uncomfortable thought. It clashes with your everyday experience. You perceive yourself as an active agent, shaping your future with your decisions. But the block universe suggests that this feeling is, well, an illusion. A convincing one to be sure, but an illusion nonetheless. But hold on. Before you descend into existential despair, let's consider some alternatives. What if the block universe isn't the whole story? What if there's something missing from the picture? Think back to entropy. We discussed how the second law of thermodynamics dictates that entropy, or disorder, always increases in a closed system. This increase in entropy is intimately linked to our perception of time's arrow. We experience time as flowing from past to future because the universe is constantly becoming more disordered. But where does this entropy come from? Why was the early universe in such a low entropy state? This is one of the biggest unsolved mysteries in cosmology. One possibility is that the low entropy of the early universe was simply a random fluctuation, a cosmic accident, if you will. But this explanation feels unsatisfying. It doesn't explain why the universe started in such an improbable state. Another possibility is that there's something fundamental about the laws of physics that favors low entropy in the early universe. Perhaps there's a deep connection between gravity and entropy that we don't yet understand. Some physicists have even suggested that the universe is constantly creating new regions of low entropy, like bubbles emerging from a sea of disorder. Now, how does this relate to free will? Well, if entropy is fundamental to the flow of time, and if the flow of time is somehow linked to our consciousness, then it's possible that our sense of agency is also tied to entropy. Maybe our ability to make choices is not an illusion, but a real physical process that's driven by the increase of entropy in the universe. Think of it this way. Every time you make a decision, you're creating new possibilities, new pathways through space-time. Each choice you make increases the overall entropy of the universe, creating a ripple effect that extends outwards in time. In this view, free will isn't just a subjective feeling, it's an objective physical force that shapes the universe itself. Of course, this is just speculation. We don't have a complete theory of consciousness, let alone a theory that connects consciousness to entropy and free will. But it's a tantalizing possibility. It suggests that our choices matter, not just to us, but to the entire universe. But what about quantum mechanics? We touched on the observer effect, the idea that the act of observing a quantum system can change its behavior. Does this mean that consciousness plays a fundamental role in shaping reality at the quantum level? Some physicists believe that it does. They argue that the collapse of the wave function, the process by which a quantum system settles into a definite state, is triggered by consciousness. In this view, reality isn't fixed until it's observed. Your conscious observations are what bring the universe into being. This is a radical idea, and it's not universally accepted. Many physicists believe that the collapse of the wave function is a purely physical process that doesn't require consciousness. But the fact that the observer effect exists at all suggests that there's a deep connection between consciousness and the quantum world. So, are we back to the idea that reality is an illusion? Not exactly. It's more like reality is a collaboration. It's a partnership between the objective laws of physics and the subjective experience of consciousness. The universe provides the stage, but we, as conscious observers, help to write the script. But even if consciousness plays a role in shaping reality, does that mean we have free will? After all, if our actions are determined by our thoughts and feelings, and if our thoughts and feelings are determined by our brains, and if our brains are governed by the laws of physics, then aren't we just sophisticated automatons? This is the age-old problem of determinism. The idea that everything that happens is causally determined by what came before. If determinism is true, then free will is an illusion. Your choices are simply the inevitable consequences of a chain of events that stretches back to the Big Bang. But quantum mechanics throws a wrench into the gears of determinism. Quantum events are inherently probabilistic. You can't predict with certainty what will happen in a quantum experiment. You can only calculate the probabilities of different outcomes. This inherent randomness at the quantum level suggests that the universe isn't completely deterministic. There's always an element of chance, a degree of freedom that allows for new possibilities to emerge. Perhaps free will is related to this quantum randomness. Maybe our brains are able to tap into the quantum realm and introduce a degree of unpredictability into our decisions. This wouldn't mean that our choices are completely random, but it would mean that they're not entirely predetermined. It's a subtle but crucial distinction. If our choices are influenced by quantum randomness, then we're not just acting out a predetermined script, we're co-creating our reality, moment by moment, in partnership with the universe. So, what does it all mean? What have we learned on this journey through space-time and consciousness? Perhaps the most important lesson is that the universe is far more mysterious and complex than we ever imagined. We've only scratched the surface of understanding the true nature of space and time. We've also learned that consciousness is likely to play a much more significant role in the universe than we previously thought. It's not just a passive observer sitting on the sidelines. It's an active participant, shaping reality at the quantum level and influencing the flow of time itself. And what about free will? The jury is still out. We don't have a definitive answer to the question of whether we truly have free will or whether our actions are predetermined. But the evidence suggests that the universe is not completely deterministic, and that there's room for agency and choice. Ultimately, the question of free will may be unanswerable. It may be a philosophical question that transcends the realm of science. But even if we can't prove that we have free will, we can choose to believe in it. We can choose to act as if our choices matter, because perhaps they do. So the next time you're faced with a decision, remember this journey. Remember the mind-bending concepts, the paradoxes and the mysteries. Remember that you are a part of this vast, complex and beautiful universe. And remember that your choices, however small they may seem, have the potential to ripple outwards through space-time, shaping the future in ways you can't even imagine. Now, what will you choose to do with that power? The universe is waiting. So, if reality, time, and even free will might be illusions, where does that leave us? Are we merely puppets dancing on the strings of some cosmic program? Or is there something more fundamental, something real beneath the surface of our perceived reality? Let's dive deeper, shall we? Imagine zooming in, not just on space, but on space-time itself. Keep magnifying past atoms, past quarks, past even the hypothetical strings of string theory. What do you see? You encounter the quantum foam. The quantum foam, also known as spacetime foam, is a theoretical concept describing the nature of spacetime at extremely small distances, near the Planck length. At these scales, quantum fluctuations are so intense that they cause spacetime to become foamy or turbulent. Imagine the surface of the ocean during a violent storm, but instead of water, it's spacetime itself constantly bubbling and churning. Think of it as the ultimate subatomic soup, a chaotic jumble of virtual particles popping in and out of existence. These aren't, quote, 58 particles in the sense that they can be directly observed for any length of time. Instead, they are fleeting quantum fluctuations allowed by the Heisenberg uncertainty principle. The principle, in essence, states that you can't know both the position and momentum of a particle with perfect accuracy. The more accurately you know one, the less accurately you know the other. And at the quantum foam level, this uncertainty extends to energy and time. Energy can seemingly borrow itself into existence for a brief moment, as long as it pays it back quickly enough. This borrowed energy manifests as virtual particles, which almost instantaneously annihilate each other, returning the energy to the void. But in that fleeting instant, they exist, and they contribute to the frenetic, bubbling nature of the quantum foam. Now, what does this have to do with space and time? Here's where it gets really mind-bending. Some physicists believe that space and time, as we understand them, are not fundamental at all. They are emergent properties arising from the collective behavior of these quantum fluctuations. Just as the smoothness of water emerges from the countless interactions of individual water molecules, so too might the smooth, continuous fabric of space-time emerge from the chaotic dance of the quantum foam. Think of it like this. Imagine a pointillist painting. Up close you see only individual dots of colour, seemingly random and disconnected. But when you step back, a coherent image emerges. The individual dots, in their collective arrangement, give rise to something greater than the sum of their parts. Similarly, the individual quantum fluctuations in the quantum foam, through their interactions and relationships, might give rise to the experience of space and time. But what are these interactions? What, quote, 60 govern the dance of the quantum foam? That's the million-dollar question, isn't it? One leading candidate for describing these interactions is quantum gravity. Quantum gravity is a field of theoretical physics that seeks to describe gravity according to the principles of quantum mechanics. The problem is, general relativity, Einstein's theory of gravity, works incredibly well at large scales. Planets, galaxies, the universe as a whole, but it breaks down at the quantum level. It predicts infinities and nonsensical results when applied to the extreme conditions of the quantum foam. Conversely, quantum mechanics, which describes the behavior of matter and energy at the atomic and subatomic levels, doesn't incorporate gravity. It's as if we have two separate languages for describing the universe, and we haven't yet found the Rosetta Stone to translate between them. String theory and loop quantum gravity are two prominent approaches to quantum gravity. String theory proposes that fundamental particles are not point-like, but rather tiny, vibrating strings. Loop quantum gravity, on the other hand, quantizes space-time itself, suggesting that space and time are not continuous but rather made up of discrete, quote, 61, quote, or loops. Both theories attempt to describe the quantum foam and how space-time might emerge from it. And both face significant challenges. String theory requires extra spatial dimensions beyond the three we experience, while loop quantum gravity struggles to fully reproduce the predictions of general relativity at larger scales. So, where does this leave us with the question of what space and time actually are? It suggests that our intuitive understanding of space and time as a smooth, continuous backdrop for reality might be fundamentally flawed. Instead, space and time might be more like illusions, emergent properties arising from a deeper, more fundamental level of reality governed by the laws of quantum gravity. Consider this. If space and time are emergent, then what is before space and time? What existed prior to the Big Bang if time itself didn't exist? These questions push us to the very edge of our understanding. They challenge our deepest assumptions about the nature of reality, and they hint at the possibility that the universe is far stranger and more mysterious than we ever imagined. But if space and time are emergent and consciousness influences reality, does that mean consciousness played a part in creating space and time? Is consciousness somehow interwoven into the fabric of the quantum foam? This is where the lines between physics, philosophy, and even metaphysics become blurred. We're not just talking about the nature of space and time anymore. We're talking about the nature of existence itself. Think back to the double-slit experiment we discussed earlier. The act of observation seems to influence the behavior of quantum particles. If consciousness is somehow linked to observation, then could it be that consciousness played a role in collapsing the quantum foam into the space-time we experience? This is a radical idea, of course, and it's one that is highly speculative. But it's also one that is worth considering, especially in light of the growing evidence that consciousness is not simply a byproduct of brain activity, but rather a fundamental aspect of reality. Maybe, just maybe, consciousness isn't in the universe. Maybe the universe is in consciousness. What if our minds, our thoughts, our feelings are not just passive observers of reality, but active participants in its creation? What if the very act of perceiving the universe shapes the universe itself? If that's the case, then the implications are staggering. It would mean that we are not just exploring the universe, we are co-creating it. This idea resonates with ancient mystical traditions that describe the universe as a manifestation of consciousness, but it also finds echoes in modern physics, particularly in the ongoing quest to understand the nature of quantum gravity and the role of observation in quantum mechanics. So, are we living in a giant simulation? Are we brains in vats, being fed a carefully constructed illusion of reality? Or is something even more profound at play? Perhaps the illusion isn't that reality isn't real, but that our perception of reality is limited. Maybe we're only seeing a tiny sliver of a much larger, more complex and ultimately unknowable reality. And maybe, just maybe, the key to unlocking the secrets of the universe lies not just in our telescopes and particle accelerators, but in our own minds. What do you think? Are you ready to take the next step and explore the potential role of consciousness in shaping the very fabric of space-time? Because believe me, we've only just scratched the surface. The rabbit hole goes much, much deeper. And next time, we are going to try and quantify consciousness. You've danced on the edge of reality, peered into the quantum foam, and felt the unsettling truth that space and time might not be what they seem. Now, prepare for a deeper dive. We're going to try to quantify something that for many feels inherently unquantifiable. Consciousness. Yes, consciousness. That elusive, subjective experience of being. The very thing that allows you to ponder these questions in the first place. Can we really measure it? Can we assign a number to the richness of your inner world, the vibrancy of your thoughts, the depth of your feelings? It sounds absurd, doesn't it? Like trying to capture a rainbow in a jar, but scientists, ever the intrepid explorers, have dared to try. And their efforts, though still in their early stages, are yielding some fascinating results. So, where do we even begin? How can you possibly start to quantify something so subjective, so personal? Well, one approach is to look at the physical substrate of consciousness, the brain. After all, it seems pretty clear that consciousness arises from the complex interactions of billions of neurons firing in your skull. Damage to certain areas of the brain can dramatically alter or even eliminate aspects of conscious experience. A stroke, for example, can rob someone of their ability to recognize faces, understand language, or even be aware of their own left side. If consciousness is a product of brain activity, then perhaps we can measure that activity and correlate it with different levels or types of conscious experience. And that's precisely what neuroscientists have been doing for decades, using tools like electroencephalography, EEG, magnetoencephalography, MEG, and functional magnetic resonance imaging, fMRI. EEG, for example, measures electrical activity in the brain using electrodes placed on the scalp. It's relatively inexpensive and has excellent temporal resolution, meaning it can capture changes in brain activity very quickly. Think of it like listening to the static of a radio. Different frequencies and patterns of electrical activity can be associated with different states of consciousness, like wakefulness, sleep, or anesthesia. fMRI, on the other hand, measures brain activity by detecting changes in blood flow. It has better spatial resolution than EEG, allowing us to pinpoint which specific brain regions are active during different tasks or experiences. Imagine it as a sophisticated weather map showing which areas of the brain are lighting up in response to various stimuli. But simply measuring brain activity isn't enough. We need a way to connect that activity to the subjective experience of consciousness. This is where things get tricky. How can you know what someone else is really experiencing? How can you be sure that your red is the same as my red? One approach is to rely on behavioral reports. We ask people to describe their experiences, to rate the intensity of their sensations, or to perform tasks that require conscious awareness. For example, we might show someone a series of images and ask them to press a button every time they see a particular shape. Or we might ask them to rate their level of pain on a scale of 1 to 10. By combining these behavioral reports with measurements of brain activity, we can start to build a picture of the neural correlates of consciousness, the specific brain processes that seem to be necessary and sufficient for conscious experience. But even with all these tools and techniques, the problem of quantifying consciousness remains incredibly challenging. For one thing, consciousness is not a single monolithic entity. It encompasses a vast array of different experiences, from the simple awareness of a sensory stimulus to the complex self-awareness that allows you to reflect on your own thoughts and feelings. Furthermore, consciousness seems to exist on a spectrum. Are you more conscious when you're wide awake and solving a complex problem than when you're daydreaming or listening to music? What about when you're asleep? Are you completely unconscious, or is there still some level of awareness present in your dreams? These are difficult questions, and there's no easy way to answer them. But one promising approach is to focus on the information processing capacity of the brain. The idea is that consciousness arises from the brain's ability to integrate information from different sources to create a unified and coherent representation of the world. This idea is at the heart of integrated information theory, IIT, a controversial but influential theory of consciousness developed by neuroscientist Giulio Tononi. IIT proposes that consciousness is directly related to the amount of integrated information that a system can generate. The more integrated information a system possesses, the more conscious it is. But how do you measure integrated information? That's the million-dollar question. Tononi and his colleagues have developed a mathematical measure called phi, which is intended to quantify the degree to which a system is both integrated and differentiated. A system with high phi is one in which the parts are highly interconnected and interdependent, but also capable of generating a wide range of different states. Think of it like this. A simple light switch has very little integrated information. It can only be in one of two states, on or off. A complex computer, on the other hand, has a vast amount of integrated information. It can perform a wide range of different tasks, and its components are all interconnected in intricate ways. According to IIT, phi is not just a measure of complexity, but a measure of experience. It's a measure of how much the system feels like something from the inside. A system with high phi is said to have a rich and complex inner world, while a system with low phi has little or no conscious experience. Now, it's important to emphasize that IIT is still a highly speculative theory. There's no direct evidence that phi actually corresponds to subjective experience. And calculating phi for a complex system like the human brain is computationally intractable. However, IIT has generated a lot of excitement in the scientific community because it offers a potentially testable framework for understanding consciousness. It makes specific predictions about which systems should be conscious and which should not, and it provides a way to compare the levels of consciousness in different systems. For example, IIT predicts that a simple thermostat should have a tiny amount of consciousness, while a human brain should have a vastly greater amount. It also predicts that certain brain lesions that disrupt the integration of information should lead to a loss of consciousness. These predictions can be tested using various experimental techniques. For example, researchers are using transcranial magnetic stimulation, TMS, to temporarily disrupt brain activity and measure the resulting changes in consciousness. They're also developing new algorithms to estimate phi in simpler systems, like networks of artificial neurons. Of course, IT is not the only theory of consciousness out there. There are many other competing ideas, each with its own strengths and weaknesses. Some theories emphasize the role of attention in consciousness, arguing that we are only aware of things that we pay attention to. Other theories focus on the role of working memory, suggesting that consciousness is closely tied to our ability to hold information in mind and manipulate it. Still others propose that consciousness is an emergent property of complex systems, arising from the interactions of many simpler components. Ultimately, the question of how to quantify consciousness remains one of the biggest challenges in science. It's a problem that touches on fundamental questions about the nature of reality, the relationship between mind and matter, and the very meaning of being. But even if we never fully understand consciousness, the attempt to quantify it is already yielding valuable insights into the workings of the brain and the nature of experience. It's forcing us to confront our assumptions about what it means to be conscious, and it's opening up new avenues for research and discovery. So, as you continue your journey through the strange and wonderful world of space and time, remember that consciousness is not just a passive observer of reality, it's an active participant, shaping and interpreting the world around us. And perhaps in the end, it's consciousness itself that holds the key to unlocking the deepest mysteries of the universe. Are we close? Perhaps not. But the journey is everything.